All right, welcome back. So it's Saturday morning. I've got a fair bit of time here. So what better thing to do than to read this textbook? So I've got my bookmark here. I'll reread the key takeaway. So decision trees, with their simple logic, are a very powerful technique. Very frequently, they are more adequate and effective than other modern and complex architectures, such as neural networks. And that's a huge takeaway. Um, yeah, so the last one was about decision trees, which is a type of. Um, hmm. Well, it's an algorithm. It's an algorithm to make yeah. So to make models. All right. So moving on to ensembles. Now that we have seen the decision trees, we will explore a few techniques that allow us to build better models. These techniques are not truly specific for regression or classification. They are pretty general. However, since we are progressively building knowledge on the previously explained algorithms, this is a logical step in the flow, even though it does not belong strictly to the regression section. We could summarize the intuition behind ensemble techniques as the wisdom of the crowd. There could be a set of individuals who are not the best experts on a particular domain, but their combined expertise and joint decision will produce a much better outcome and likely outperform a powerful expert individual. An ensemble method results in a combination of multiple models, possibly weak performer models, providing a much better prediction or classification performance. There are various methods. We will now describe a few of them with examples of algorithms that use such methods. The focus will be more on intuition rather than on mathematical explanation. So the first method for for this sort of thing, for an ensemble, for getting the wisdom of the crowd, is bagging. Bagging. Bagging means bootstrapping and aggregation. Let me explain each part. Bootstrap. Bootstrapping is a data sampling technique. It allows us to pick a sample from the input dataset. Multiple samples will be extracted, and each will feed a different model. The random samples are extracted with replacement. That means one observation could be repeated several times on the same sample. Aggregation. Each sample will be used to train a weak model, but the result of these models will be aggregated using a voting system. The expectation is that each model will be able to learn specific characteristics of the data, and the aggregated result will be able to perform well in terms of accuracy and ability to generalize. So I like to feed these into ChatGPT to see what it has to say.
It looks like you've uploaded an image that illustrates a machine learning ensemble technique. How can I assist you with it?
All right, so I'm reading a book called Machine Learning for Network and Cloud Engineers. I like to just paste these when I see them into ChatGPT to help me understand the stuff I'm reading in the book. So I guess just to read it through and like explain the image to me and like why it's important and like just know out some basics and like bring me up to speed on the concepts.
The image you've uploaded depicts a common machine learning ensemble technique known as bootstrap aggregating, commonly referred to as bagging. This method is frequently used to improve the stability and accuracy of machine learning algorithms. Let's walk through the image and its components to understand how bagging works and why it's significant. Fill input dataset. This is the original dataset you have available for training your models. It typically consists of numerous data points, each with its own set of features. Bootstrap. The process begins by creating multiple samples from the original dataset. This sampling is done with replacement, meaning the same data point can appear in a sample more than once. Each sample is likely to be slightly different from the others due to the randomness in the sampling process. Model training. Each Bootstrap sample is used to train a separate model. Although the diagram labels each model as Model 1, it typically refers to multiple instances of the same type of model, each trained on different data. The idea is that by training each model on slightly different data, the overall model, when combined, is more robust and less likely to overfit the noise in the training data. Aggregation. Voting. After all the models are trained, their predictions are combined to produce a final result. The method of combination depends on the type of task. For classification, it's common to use majority voting, where the predicted class is the one that receives the most votes from individual models. For regression, the aggregation is typically the average of the predictions from all models. Why is bagging important? Bagging is particularly powerful in reducing variance, preventing overfitting, and improving the accuracy of models, especially for those that tend to have high variance like decision trees. By averaging several models, the effect of outliers and noise is minimized, making the final prediction more reliable. General benefits of ensemble techniques like bagging. Robustness. Combining multiple models tends to cancel out individual errors. Improved accuracy. Ensemble models often perform better than any single model. Overfitting reduction. By using multiple subsets of the original data, the ensemble is less likely to learn noise in the data as signal. Understanding and applying bagging can significantly improve the performance of your machine learning projects, especially in complex fields like networking and cloud environments, where data can be diverse and inconsistent.
Alright, so moving on. One of the most popular algorithms in this category is random forest, which uses decision tree as the basic model to aggregate. The next one is boosting. Before describing the fundamentals of the technique, let me digress for a moment. K. Anders Ericsson, in his book Peak, where he analyzes the secrets of high performance in any discipline, explains that the key ingredient is what he calls deliberate practice. It is not enough to repeat a process to master it. There have to be specific. Oh no, half is probably right. There have to be specific practice actions designed to improve certain subtasks or eliminate specific weaknesses. The effort must be deliberate and explicit. What has this to do with machine learning? A lot. Many techniques and practices in machine learning are simply inherited and ported from either nature or human behavior. In this case, our goal is to build an ensemble model that can perform much better than any individual. What would you think is the weakness of a particular trained model? The observations where it fails. If that is the case, you could think of the observations where it fails. So what would you think is the weakness of a particular trained model? The observations where it fails are the weaknesses. If that is the case, you could think of somehow training a new model where those observations are given more importance so that you could make a deliberate effort to force such a new model to improve. The resulting model will still fail, very likely, in some observations. Why not repeat the process? So the result is a set of trained models, one after another, addressing the weaknesses of the previous one in a more deliberate approach. Combining all those models will result in an ensemble that performs much better than its models alone. So I got a name, so when I get names like that, I like to take a look if it makes sense to add them in LinkedIn. Now this is just an author. Yeah, this is just an author, so I don't think oh, yeah, so here's someone producing content about this person. But yeah, I don't think I'm gonna add anyone on LinkedIn for that. Alright, so now I will feed this into ChatGPT. That's so cool that it knows, it's able to know what it is. So this is boosting. Like, it'll know
The
that
second
it's
image you
boosting.
uploaded illustrates another common technique in machine learning ensemble methods, possibly showcasing how an ensemble model is validated and how the predictions from various models are aggregated to obtain a final result. Here's a breakdown of the process depicted in your image. Fill input dataset. Similar to the first image, this represents the original dataset from which samples are drawn. Sampling. This process involves creating multiple subsets, samples 1 through n, from the original dataset. Each subset is used to train a different model. The sampling can be with replacement, like in bagging, or without replacement, depending on the technique. Model training. Different models, model 1 through model n, are trained on these subsets. In this image, unlike the first one, each model can be of a different type or the same type but trained independently on different samples. The models generate predictions on a set of test data not seen during the training phase. Error calculation. For each model, predictions are made on the test data and the error of these predictions is calculated. This step is critical for understanding how well each model performs independently. Aggregation. The final predictions of each model are then combined to get a final result. This aggregation might involve averaging the predictions, taking a weighted average based on model performance, or other methods to minimize the overall error. Final result. The aggregated prediction aims to leverage the strengths of each model to provide a more accurate and robust prediction than any single model could achieve. Importance of this process. Validation. This method shows a clear process for validating each model against a test dataset, which is crucial for assessing model performance. Reduction of overfitting. By testing each model independently on unseen data, it's possible to gauge whether the models are simply memorizing the training data or genuinely learning underlying patterns. Enhanced accuracy. Aggregating predictions usually leads to better performance because it combines the predictive power of multiple models, thereby often reducing the impact of any single model's bias or variance. This kind of ensemble learning is essential for improving predictions in many real-world applications, where the complexity and variability of data can make it difficult for a single model to perform consistently well. It's particularly valuable in fields like networking and cloud engineering, where systems must be robust and highly adaptive.
Based on the image, do you know the name of the technique? Boosting. Oh.
Based on the description in the diagram in the second image you uploaded, the technique depicted is likely cross-validation used in conjunction with an ensemble learning approach. Here's why. Multiple models and datasets. The process involves training multiple models on different subsets of the data. This is characteristic of both ensemble methods and cross-validation techniques. Error calculation. The inclusion of an explicit error calculation step for each model's predictions on test data hints at a cross-validation setup, where each model is evaluated on a separate part of the dataset not used during its training. Aggregation. The aggregation of predictions from multiple models to form a final result is a hallmark of ensemble methods. In cross-validation, particularly in a method known as stateful cross-validation, this step might not typically involve combining model predictions but rather averaging performance metrics. However, in ensemble learning using cross-validation, the final ensemble's prediction can indeed be derived by aggregating outputs from each fold model. Clarification. Ensemble learning. Techniques like bagging or boosting where multiple models are trained either on the whole dataset or subsets, and their predictions are combined. Cross-validation. A model validation technique to assess how the results of a statistical analysis will generalize to an independent dataset. It is primarily used in settings where the goal is to forecast and one wants to estimate how accurately a predictive model will perform in practice. If the setup involves using cross-validation folds to train individual models and then aggregating their predictions, it could be an instance of a technique like stack generalization, stacking, where the final model or meta-model is trained on the outputs of other models, each trained in a different fold of the dataset. This technique is powerful for reducing bias and variance, as it combines the strengths of multiple learners.
Is there anything about the image that would make it more clearly a boosting technique rather than a bagging technique?
The image you've shared does not provide explicit details that definitively suggest it represents a boosting technique rather than bagging.
Interesting.
However, let's differentiate the two concepts to clarify potential indicators. Boosting sequential model training. In boosting, models are trained sequentially, with each new model being influenced by the performance of those preceding it. Each subsequent model focuses on data points that were previously misclassified or had higher errors. Weight aggregation. In boosting, the predictions of the models are not typically given equal weight in the final decision. Instead, models that perform better, i.e., have lower error rates, are given more influence in the final prediction. Error focus. Boosting specifically adjusts the weights of incorrectly predicted instances so they are more likely to be correctly predicted in the next round of model training. Indicators from your image error calculation. The image shows that an error is calculated for each model's predictions. This could hint toward boosting if these error calculations influence subsequent model training or weighting in the aggregation phase. Aggregation method. The diagram notes an aggregation phase but does not specify how it occurs. In boosting, this would typically involve weighting models based on their accuracy. Reasons for ambiguity model independence. The image suggests models might be trained independently, like in bagging, as there is no explicit connection or sequential adjustment shown between the models based on their performance. Parallel versus sequential. The models appear to be trained in parallel, more characteristic of bagging, not sequentially, which is a key feature of boosting. Conclusion. Without clear indications of sequential training and adaptive weighting based on performance, it's challenging to definitively classify the technique in the diagram as boosting. It more closely aligns with the generic ensemble method, possibly incorporating elements of cross-validation. To be boosting, we'd expect to see a clear depiction of sequential training and differential weighting based on model accuracy.
All right. Okay, so moving on. This technique builds on the weaknesses of the previous model to train a new one that can be slightly better so that the aggregated result is a combination of models that collectively complement each other and provide a more accurate result. Various algorithms, such as AdaBoost, leverage this technique, and the very important XGBoost. XGBoost has proven to be one of the most powerful and flexible techniques, a preferred choice of many winners in the Kaggle challenges. The Kaggle challenges. Stacking. In bagging and boosting, we have in both cases presented some aggregation at the end of the result from the various models involved. Whether a voting mechanism, a sum, a mean, etc. Somehow this starts with the assumption that such aggregation choice is the best, but what if it is not? What if the aggregation mechanism depends on the values themselves? We could think of a cascaded stacked model that uses the output of the previous models as an input. This is the basis for the stacking technique, the ability to stack new models on top of the previous ones and train them with the output, predictions or classifications of the previous ones. The model will learn how to do the optimal aggregation between the previous models rather than simply doing a basic mathematical operation, voting, mean, average, etc. This approach is very similar conceptually to the different layers that are stacked in a neural network, but the training process is entirely different. In the stacking approach, each layer is an independent model that is trained. In the neural network approach, all layers belong to a unique model that is trained as a whole. We will see this later in detail. So we've got a new model. Let's put it into ChatGPT.
The new image you uploaded illustrates the concept of stack generalization, commonly known as stacking. Stacking is an ensemble machine learning technique that combines multiple models to form a new model, aimed at reducing bias and variance and improving predictions. Here's how the depicted process works. Total input dataset. This is your complete dataset used for training various base models. Multiple base models. Different models, model 1, model 2, model n, are trained independently on the same dataset. These models can be of various types, such as decision trees, support vector machines, neural networks, etc., depending on what fits best with the data characteristics. Model predictions. Each of these models makes predictions based on the input data. These predictions are then used as input features for the next layer of the model. Meta-model. Instead of simple aggregation methods like voting or averaging, stacking uses these base model predictions as input features for a final model, known as a meta-model. The meta-model is trained on these predictions to learn the best possible way to combine them to make a final prediction. Final result. The prediction from the meta-model is considered the final result of the ensemble method. This result is typically more accurate and robust than what could be achieved by any single base model. Importance of stacking. Performance improvement. Stacking can outperform individual models and many other ensemble techniques because it leverages the strengths of each base model and effectively combines them. Diversity of models. Stacking encourages the combination of different model types, potentially capturing varied patterns in the data that a single model or homogeneous ensemble might miss. Model robustness. By using a meta-model, stacking can adaptively learn which models are providing the most valuable insights, allowing for a dynamic and effective combination of predictions. Stacking is especially valuable in competitive machine learning and in scenarios where the stakes for accurate predictions are high, such as complex regression tasks or classification problems with intricate decision boundaries. It's a sophisticated technique that requires careful implementation to avoid overfitting, especially in how the meta-model is trained and validated.
Alright, so the key takeaway is XGBoost is the best performing algorithm for a large majority of use cases. The next section is neural networks. But before I move on, I would like to pull up Kaggle, because I've heard about Kaggle before. My understanding of Kaggle is it's basically like LeetCode, but it's LeetCode for data science and AI and machine learning. So Kaggle is pretty important. I do have an account on Kaggle, I believe. So I'll sign in with my account. And I believe I do have some activity on my account if I go to my work. Maybe I tried doing it with another account, but yeah. So you can do AI to you can create your own competitions. You can host competitions. So it's like LeetCode. Yeah. Cool. I should be spending more time on Kaggle. Yeah, so if you go to the Learn tab here, now we've got some courses. I feel like, so Python basically, one of the best use cases for Python is data science. So I feel like the best way to learn Python is to do it in the context of data science. So this would be a great tutorial for anyone new to Python. And this might be something I want to do later. So I'm gonna bookmark this. under another folder. I'm going to bookmark it under my career folder. And I'm going to bookmark it under technical development courses. Actually, under AI. Okay, there we go. All right, so moving on. There is a section in the book focused on neural networks, so I will not describe them here. I will only mention here the fact that neural networks are a powerful technique for regression or prediction problems, as well as classification. I want to ensure you understand that when it comes to regression techniques, neural networks are a crucial piece of the puzzle in many use cases. More frequently, the more data available and the more complex the problem is, image, video, audio, natural language, etc. That's when you need to use neural networks. All right, so next section is classification techniques. I need a quick break here. All right, I'm back, so let's keep going. We're going to move on to classification techniques. Regression is about predicting a real number out of a continuous space. Classification is about predicting a class or category out of a discrete and defined set of options. There is an important factor to understand and differentiate. While regression implicitly requires that the output is ordinal, for example, there is an order in the variable, 3 is more than 2, or 2.1 is closer to 2 than 3. In classification, the output is categorical. There is a set of options as output, but there is no ordering on them, and none is numerically closer. For example, like a cat versus a dog. Let's review a few new concepts that, while not specific to the classification versus regression discussion, are now relevant and you should have a good understanding. As you can see, I'm trying to introduce concepts progressively as needed. In machine learning, algorithms need to be fed by numbers. All models ultimately rely on statistical techniques or other formulations, but they only work with numbers. So, regardless of our data source, we need to build the proper representation of the data in numbers to feed our models. As part of that representation, we may need to perform additional transformations, as explained in the polynomial regression section. Let's consider the example earlier in the book where we had 500 network metrics as input. Let's review some examples of types of metrics. Memory utilization in a server. This is an example of a quantitative and continuous variable. It can take any value within a range, in this case possibly, and there is a sense of natural order. Operating system name in a router. This is an example of a categorical and nominal because the version of the operating system. There are a set of options in your network. Consider iOS-XR, Junos, SROS, EOS. There is no specific order in them, and the set of options is discrete and well-known. Software version in an Arista switch. This is an example of a categorical and ordinal. Examples, so we've got 4.15, but then we've got the numbers changing as new versions are released. They are discrete, but there is some sense of order that could be used to represent the information. So you can determine whether it's old or new by using ordinal, an ordinal evaluation. Type of network failure. Example of a categorical and nominal variable. Examples of it could be the following list: OSPF issue, BGP issue, hardware issue, software issue, ISIS issue, interface down. Number of ports used in a switch, numeric and discrete. The number of ports will always be an integer and positive. Effectively, we can find 4 types of data we may need to manage or transform: numeric and continuous. Like on the memory utilization above or interface traffic, typically these are presented as real numbers and they are already in a form factor that is machine learning model friendly. So these are numeric and continuous. We may still need to apply certain transformations, such as scaling or normalization, if applicable. If our predictive model has this variable as an output, very likely it will produce the value right away, even though we may need to apply a descaling or denormalization transformation if we had applied it in the input of the model. Number 2, numeric and discrete. As input data, as long as it is numeric and has the right scale, this variable type will be model friendly as well. Note though, the scaling / normalization transformations will likely turn the integer number into a real number. Similarly, the output of a regression model will not be an integer. Most of the statistical and mathematical transformations that happen within a model cannot guarantee the discrete nature of integers, neither inside nor as the output of the model. We can, though, as the final step in the data presentation or subsequent analysis, apply a round function that will eliminate the decimals and present the result in a more meaningful way. In our example of the numbers of ports variable, very likely it will be a round underscore up function. Categorical and nominal. This type is applicable when the set of options for the variable is discrete and follows no particular order. The values may be represented in text or any other form factor which are not machine learning model friendly. Therefore, we need to transform them into numbers. There are different techniques. The first technique is to create a dictionary. Very frequently, if we have 10 different options for a certain variable, we can create a dictionary that assigns a number to each of those options and then use that index as the data representation for the machine learning processing. One challenge for this approach by itself is that it may create a sense of order or distance that is not real, which could mislead the model. So I'll plug that into ChatGPT.
The image you've uploaded illustrates a method of encoding categorical data, specifically for problem types in networking context, into a numerical format that can be used for machine learning models. Here's a breakdown of each component in the process. Component problem type. This lists various issues that can occur in network, such as OSPF issues, BGP issues, hardware issues, etc. Dictionary. This is a mapping of each problem type to a unique integer. This kind of mapping is crucial for converting categorical data into a numeric format that machine learning algorithms can process, since most algorithms require numerical input. Input data. This shows an example of how a set of problem types, listed as OSPF issue, hardware issue, optics issue, interface down, are converted into a list of corresponding numerical codes, 1, 3, 8, 7, based on the dictionary provided. Process and significance categorical encoding. This process is a typical example of categorical encoding where categories, textual data, are converted into numbers. This conversion is necessary because machine learning models fundamentally operate on numerical data and cannot directly process text data. Vector representation. The numerical list represents the input vector for a machine learning model. Each number in the vector refers to a specific type of network issue according to the predefined dictionary. Utility in machine learning. Encoding like this helps in various ways. Model training. The numerical codes can be used as features to train machine learning models to predict network failures, classify the type of network issues, or trigger automated responses. Data simplification. It simplifies the dataset by converting diverse problem types into a standardized numerical format, which is easier to manipulate and analyze statistically. Scalability. With numerical coding, adding new categories, e.g., a new type of network issue, becomes manageable by merely extending the dictionary, without altering the overall data structure. Applications this kind of categorical encoding is widely used in fields beyond networking, like natural language processing, customer segmentation, and any other domain where categorical data needs to be used in statistical models. In your context, such encoding will be crucial for developing predictive maintenance systems or automated troubleshooting tools within networking infrastructure.
All right, so moving on to the next one, which is create a one-hot encoding. This is about transforming each categorical variable into a set of binary variables, as many as different values that the categorical variable may have. If we have 7 different possible values, there will be 7 different one-hot encoded variables, which will be 1 or 0. In this case, we have transformed our input variable into a set of numbers, 1 or 0, and there is no sense of order or distance. On the other hand, sometimes this may trigger challenges because it may increase substantially the number of input features in our model and increase the complexity and size, particularly in this case with input data that will be very sparse, mostly zeros and very few ones. There are also techniques used to deal more efficiently with very sparse matrices like the ones resulting when we apply one-hot encoding. So let's take a look at this.
The new image you've uploaded depicts another method of handling categorical data, specifically using one-hot encoding. This is a common data preparation technique used in machine learning to handle categorical variables. Let's examine each part of the image. Components problem type. A list of different problem types similar to the previous image, including various network issues like OSPF issue, BGP issue, and others. New variables. For each problem type in the list, a new binary variable column is created. Each variable corresponds to one problem type. Input data. This shows how multiple problem types are represented in binary format. For each problem type, a 1 is placed in the column corresponding to that issue, and 0 is replaced in all other columns. The example provided in the image transforms the list of problem types from the dataset OSPF issue, hardware issue, optics issue, interface down, into a binary matrix representation. Process and significance binary encoding. In one-hot encoding, each categorical value is converted into a new binary variable and assigned a 1 or 0. For example, if OSPF issue occurs, the column for OSPF issue will have a 1, and all other problem type columns will have 0. Sparse matrix. This method often results in a sparse matrix where most of the values are 0. This matrix effectively captures the presence or absence of each category without imposing ordinality, i.e., the notion that one category is greater than another. Utility in machine learning. Avoiding bias. Unlike label encoding, which assigns a unique number to each category and can inadvertently introduce a relational bias between categories, one-hot encoding treats each category as an independent feature, avoiding this issue. Model readiness. Many machine learning algorithms perform better when categorical data is transformed into numerical data. One-hot encoding provides a straightforward method to convert qualitative data into a form that can be processed by these algorithms. Compatibility is particularly useful for algorithms that expect continuous input and cannot interpret categorical data, such as linear regression and logistic regression. Applications. One-hot encoding is widely used across various applications where categorical features need to be fed into machine learning models, including customer analytics, recommendation systems, and predictive maintenance models in network engineering. In network settings, such encoding allows models to precisely identify and react to specific issues without assuming any inherent order or priority among them unless explicitly modeled. Overall, this image shows a clear and efficient method to prepare categorical network issue data for complex machine learning models, enhancing the ability to analyze and predict network performance issues based on historical data.
All right, so every input observation is transformed into a vector with as many columns as new one-hot encoded features have been created. Such a vector will only have 1, so a 1 or a 0, in this case 1, corresponding to the actual value of the original feature, and the remaining columns will be 0. Now we can train our models with this matrix as input. As an output, a categorical variable will not result directly in 0 or 1, but we can round the number to the closest. Frequently, the output of a model will be a vector of probabilities, where each position represents the probability that it is the correct answer. Usually we will pick the max value as the right choice and set that position in the vector to 1, and the remaining ones will be set to 0. Now that we have identified how categorical variables need to be transformed, we are ready to tackle classification problems. A classification problem is a machine learning problem where the target label, let us remember we are in the supervised learning context, is categorical, a class or category, rather than numerical. with a quantity. And in that case, it would be continuous. In this case, it is discrete. We want the model to be able to classify new observations into any of the target categories. In the simplest form, the class will be binary yes or no, dog or cat, spam or not spam, etc. In that case, we can simply transform the variable into one column. Earlier, we said that we need as many one-hot encoded columns as values the categorical feature may have, but strictly speaking, we need one less. So now our classification model will aim to produce a 1 or a 0 as a classification task. A number between 1 and 0 is, in practice, a probability number. When we have multiple classes, a model is expected to produce a 1 for the suitable target class and a 0 for the remaining ones. We will be training our model in practice to produce a probability number between 0 and 1 for each possible answer. We will pick the class that has the highest probability among all. There are multiple algorithms for classification problems. Many of them have been introduced in the previous section because the internal machinery for classification and regression has many commonalities. Consequently, the same algorithms can be used with some exceptions. You could think there are exceptions, though, that a classification problem is a regression problem for the probabilities of the target classes, so it all comes down to solving a regression. Key takeaway: data representation is a fundamental pillar for any machine learning project. We need to make the right choices in order to make sure the information our data contains is truly represented and the ML model can extract it. Alright, so the next is pretty involved, and I have kind of a cutoff. I could do, but you know what? I don't want to be rushed before my next thing, so I think this is a really logical stopping point. So thanks for watching, and stay tuned for the next video, which is about the k nearest neighbors, KNN, and this is a classification technique.